It is my pleasure to introduce Professor William Kahan, who's a retired professor from the University of California at Berkeley. He is famous for many things, including the invention of floating point standards and the many ways that one should be using floating point to best advantage. And today, Professor Kahan will be talking about debugging tools for floating point programs. So Professor Kahan, I'll give you the stage.
Thank you. When the IEEE standard was formulated back in 1980, there were various features that were added to help debugging floating point, because floating point codes are really very, very different from other codes. And the trouble is that there weren't enough people who appreciated what those features were to get them to be supported by language designers and implementers, and by some folks that had to work on the operating systems. Well, maybe if I go through some of the examples here, some people will think about this again and decide that maybe it is worth supporting these things. How does a floating point program differ from the others? Well, the trouble is that when you write the text of your program, that's not the program you get, because the program you get is going to be afflicted by rounding errors, which are very hard to avoid, and by certain kinds of exceptions, none of which appear in the text of your program. So you don't get the program you wrote. Now, there are a number of other disparities that distinguish floating point programs from others. One of the most perplexing in some ways is that accuracy is not transitive across the composition of floating point programs. I'll give you an example of that in a moment. And then, of course, I mentioned that floating point arithmetic is generally afflicted with rounding errors. Every arithmetic operation gets rounded to finite precision, maybe not as much precision as you really would like to have. And then there's the risk of various exceptions, things like overflow and underflow. And there are other exceptional events that occur. They're not written in your program. They just happen. There are exceptions like division by zero. They're not always errors. In an integer program, division by zero is certainly an excuse to stop the program. But in floating point, no, sometimes there are good reasons for dividing by zero. And then finally, there's either optimizations. The program that you get has been optimized to improve its speed. But sometimes the way you improve the speed that would work for integers doesn't work properly for floating point. The code will run, but then it will not necessarily do what it ought to do. There is a common misconception. A lot of people believe that floating point is afflicted by catastrophic cancellation. It's a word you've heard. What about enormous intermediate results? Because in floating point, you can get some very, very big numbers. And then, of course, there are the rounding errors, vast numbers of rounding errors. And many people think that these are what cause floating point programs to malfunction. Actually, it's not quite that. It's perfectly possible to have a program which gets utterly the wrong answer, despite that there are no add subtracts, so there are no cancellations. There are no divisions, no transcendental functions, so you can't get enormous numbers. And there's only a couple of hundred or 300 algebraic operations, and that's not really very much nowadays, so you can't say that there are hordes of rounding errors. I'm not going to go into the details of that. There's a citation at the bottom of the screen which tells you where to go and look for that program. But it is something that causes trouble. Well, let's look at the first problem, which looks as if it was a deal breaker. Correctness is something that's transitive across the composition of programs. If you have a program that's correct and its output can be input to another program and it's also correct, when you put the two programs together, head to tail, you still have a bigger correct program. That doesn't quite happen with floating point. Here's an example. I'm going to look at three functions. There is a function g, a function h, and when you compose g and h, so f of x is g of h of x. If g and h are accurate, correct within a couple of units in the last place, well, shouldn't f be accurate? And the answer is not necessarily. Here are the formulas. And what I'm going to do is show you the graph. The correct composition of the program would do. But what you can see is the steps. It looks as if there are steps going up there. Well, that's the graph of the composed program. And as you see, the errors are pretty big. So there's our first problem, that correctness, it can follow, but accuracy does not necessarily follow. Now, it's a good thing that this doesn't happen all the time, because if it did, we would find that numerical software would be impossible, because numerical software is a cooperative venture. We often incorporate other people's programs in our own floating point programs. And if we would lose accuracy just from composition, well, that would be a disaster. So fortunately, the disaster happens only very rarely. In fact, sometimes you believe that you have to make up these artificial examples in order to get it to happen. Round off is the big problem. That is always with us, and it can be extremely difficult to deal with. Now, attempts have been made to automate error analysis. One such attempt is interval arithmetic. Interval arithmetic, you represent every variable by an interval that contains the true value of that variable. And then if you combine two variables in an arithmetic operation, well, then the result of that arithmetic operation is something that must include all the possible values that you get from these two interval variables. Now, the trouble is that this type of scheme, and there are lots of variations on this scheme, this kind of scheme does not work properly for lengthy programs or complicated ones. What goes wrong? Well, you end up with huge intervals. The intervals do indeed include the true values that you wish you had computed, But the trouble is, intervals include an awful lot more. There are ways to find out about this. And it's possible. It's possible in some cases to make interval arithmetic work by doing something rather subtle. Instead, what I suggest that you do is run a program 4 times, each time directing the rounding errors in a different direction, because the IEEE Standard says you can, at least in principle, you're allowed to say, I want to round everything up, or I want to round everything down. Or maybe I'd like to do it again, rounding everything towards 0. And the 4th way is rounding to nearest, which is the default. Now, it turns out that this very often gives you an idea of how uncertain your result is because of round off by looking at the 4 different values and looking at how far apart they spread. I tell you what, let's look at an example. Now, this example is an imaginary astronomical observatory, which is in orbit around the sun, but its orbit is perpendicular to the ecliptic. So it gets far away from the orbits of the planets and then comes back close to the orbits. So it's continually varying in its distance from the planets and asteroids. Now, of course, astronomical objects have minds of their own, and they do not follow exactly according to Newton's laws because of perturbations from other astronomical objects. So every now and then it's necessary to look at stars or planets through a telescope, and by assessing the positions, it's really the question is, what is the angle that you have to look at 2 different objects, 2 stars or 2 planets, and from that angle and a few others like them, you'll be able to figure out where you are. And then if you don't like where you are, you try to use a little bit of fuel to move yourself back to the proper orbit. What we're trying to do is look at the angles that are subtended at the telescope by the directions to stars that are listed in your ephemeris. The angle subtended gives you some idea of where you are. And if you get a few of these angles, you can figure out very accurately where you are. But it takes a computation. And 3 contractors have offered software to do the computation of the angle subtended at the telescope. The names of the angles are sometimes azimuth and elevation, or right ascension, inclination, and so on. These are different names used for different applications of spherical coordinates. But the main thing is you're going to get 2 angle measurements for each star or planet. And from those 4 angles all told, you'd like to get some idea of what the angle that's subtended at the telescope. Well, it turns out that that's an interesting computation.
Can I just ask a question? Are the 6 columns there, are those just 6 different stars?
There's 6 different pairs of stars.
Okay.
After all, the names of the programs are U, V, and W, each from a different contractor. And these are 3 ways to compute the angle psi that's subtended at the telescope. And so there are 6 instances of pairs of stars. The angles are shown. Theta and phi are the angles. But it turns out that it's the difference between the 2 theta values that really matter. So that's why there are only 3 rows that show us where theta and phi arise. And then the bottom 3 lines are the angles subtended at the telescope. That's psi. And they're computed in 3 different ways. And the 3 different ways sometimes disagree. And you can look at the red digits. They turn out to be wrong. And the question is, how do I know which digits are wrong? Well, that is something we're going to have to test. So I'm only taking 2 of the samples instead of 6 samples. The 2 samples I'm going to look at are the ones between pairs of dark parallel lines, vertical lines. Those are the ones I really want to look at more closely. What you're going to see is 4 different ways of computing the subtended angle. Each way runs the contractor's program, but with different rounding directions. So there are 4 different rounding directions, and therefore each contractor has what amounts to 4 different results. When you look at these results, you can see, let's take a look at the first psi computed by a contractor whose program's name is U. You can see 3 values because you can round to 0, to plus infinity, and to minus infinity. And that's the spread that you get. You get 3 different values, and you can see that the 3 different values disagree. The one that says NaN, N-A-N, that's not a number. And the reason that you got not a number was because in the formula that contractor used, these particular values led to an arc cos of a number bigger than 1. And that's an invalid operation. But you can see that some of these guys lose quite a few digits, and some lose just a few digits. But the formula W, that loses very few digits, fewer digits than the others. And we know about that because that's the spread. The different rounding directions get different results. And if they're very different, then that means that rounding errors must be contributing an awful lot of noise to the calculation. So we can now decide that it's contractor W. His program seems to be accurate. Now, I think you'd probably be a little bit curious. about which programs get these rather different results. And I have that on the next page. Okay. The subprogram U, which can lose all of its digits sometimes, that's a formula that would be obtained for the subtended angle if you just use the obvious trigonometric formulas. The kind that some people learn in high school and others learn in college. Subprogram V, that doesn't lose quite so many figures, but it still has a certain amount of work. You can see that there's an arc sine and a cos. So that's 3 references to trig functions. And then subprogram W. Well, subprogram W seems terribly unobvious. Where did that come from? It has an arctan and a tan. So it has fewer references to the math library, 2 instead of 3 or 4. And it's much more accurate. But where did it come from? Well, it comes from people who have learned something about numerical analysis and have some idea of what causes worse rounding errors. It's possible to prove that the first program can lose all of its digits, the second program V can lose half of its digits, and the third program W can lose only a few digits. That can be proved. So it's nice to know that we get some corroboration. I'd like to try a different example now. I'm having trouble here changing pages because every now and then the little arrows get covered up. Okay, this is a different kind of program. It's about a vibrating elastic structure. Now, this structure has no friction, which of course is quite fictitious, but that doesn't matter because the low frequency modes of vibration are the ones that tend to persist, whereas the very high frequency modes, which are computed less accurately, they tend to dissipate. The usual formulas for doing this, which assume no friction, although they're fictitious, it doesn't matter because although friction damps the very high frequency modes of vibration, they also have lower amplitudes, and so we won't really worry in this instance. But of course, in general, it's necessary to take friction into account. Well, okay, so here's an idealized vibration problem. And as you can see, there are straightforward ways to solve the problem. The 2 matrices A and M, they're both symmetric and for stable situations, positive definite. Those matrices can be factored. We factor the matrix M into a product of triangular matrices. U is an upper triangular matrix. U transpose U is the factorization of M. And then we have to invert the matrix U. Well, it's a triangular matrix. It doesn't take much work to invert it. And we now form U transpose inverse A, U inverse, that's in the middle of the page. That's the guy whose eigenvalues we want to compute. Then we'll take those square roots to get the frequencies. And that's where we get the modes, the vibrational mode, the shape of the structure as it vibrates. That's vector B, and it's obtained from U inverse times an eigenvector C of the matrix U transpose inverse A U inverse. And MATLAB has a program that does that. And now the question is, how accurate is it? Well, it turns out that if the matrices A and M have very nearly null spaces, that is to say, if there are vector subspaces that are almost annihilated by both matrices, then it turns out that you're going to get a rather inaccurate result. But of course, you might not know that. Well, you can find out. And here's how you find out. Okay, first, let's get the data. I want to put the data into the computer exactly. I don't want the corruptions of data to add that error to the computation, because then we won't know what's responsible for the error. So it turns out that there's this integer L at the top of the page. That's the least common multiple of the integers from 2 to 20. And what we do is we divide that integer, the big integer, by little ones, and we get quotients that are exactly integers. And so the elements of A and M are entered into the computer exactly. They turn out to be integers, but they're not too big. So the quotients are computed exactly, even though it's floating point. And therefore, A and M have exact values. Now, any rounding error problems, that will be caused by the algorithm that we use to do the computation, not caused by the fact that the data is uncertain, because it's not. Now, naturally, we're going to compute the 10 eigenvalues. That's lambda mentioned at the bottom. We're going to compute the 10 eigenvalues in 3 ways, in addition to matrices A and M factored, etc. We're going to do it in 3 ways. First of all, there's the MATLAB program that computes the eigenvalues of this pair of matrices. And then what we'll do is reverse the rows and columns. Now, it turns out that reversing the rows and columns should not change the eigenvalues. And then we'll just reverse the elements of the eigenvectors. So that means we have 2 different ways to do the computation. And then there's a third way. That's in the middle of the page. That's V. This is a singular value decomposition of a matrix F. And then we square it. And that turns out to give us the same eigenvalues. It's not obvious. In fact, it's extremely unobvious. But it turns out to be an interesting thing, because the computation U, that's doing it the way I described, where we factor the matrix and stuff. W does the same factorization, except that the rows and columns are reversed. And V is this bidiagonal matrix whose singular values turn out to be rather convenient. It's not easy to see, but F is a diagonal matrix of square roots and multiplied either side by a bidiagonal matrix. And that can be computed pretty accurately because although the square roots get rounded, the rounding error is just in the last digit. And the middle matrix, the bidiagonal matrix, its elements are all integers. So when we multiply all these things together, the rounding errors are going to be in this the last few bits. And then after computing singular values, which can be done quite accurately, we square them and compare them with what we got from the more conventional ways. It turns out that V, the singular values squared, they're pretty accurate. And that's corroborated by the fact that if you change the direction of rounding and repeating, just use a different rounding direction, it changes things by something like 10 to the minus 16. Numbers which are of the order of 1 get changed by 10 to the minus 16. But the conventional way of doing the job, you still get numbers that are of order of magnitude 1, except for this guy down here, which is rather big. You can see that the variations in these elements, the spread among different ways of computing, different in direction of rounding. That spread is something of the order of, well, it's like 4 down here. That's rather unusual. But the other spread is something of the order of 0.0, 0.05.
Should we be concerned that these deltas are not on the order of 10 to the minus 16th?
The deltas in V computed from squared singular values, it's possible for you to do an error analysis to show that they're about right. They may be a little bit optimistic because rounding errors are rounding errors, honest to God rounding errors are comparable to these values. So all you can say is that you've got a rough idea of the spread, which encompasses the variations due to round off. But in the other cases, U and W, those spreads are enormously bigger than you might have expected from round off, but they're deserved because the data has an unfortunate property. The matrices A and M almost share a null space. And for that reason, the computation gets corrupted. It's like ill-conditioned. It's a terribly ill-conditioned problem. And now you've corroborated by recomputation. You've corroborated what an error analysis would tell you, except of course that the error analysis is very much more pessimistic than this computation, but not so much more pessimistic that you'd be upset. Well, I've given you 2 examples. On my webpage, you'll find in various places other examples where I run a computation 4 times and I get a spread. Now, you'll also find on my webpage an instance where you don't get any spread. It's possible to be fooled. Redoing the computation 4 times with different directions of rounding, it's not foolproof. There are rare instances, one could almost say, where the scheme doesn't work. but I didn't promise something that was foolproof. You see, we don't have a way to estimate rounding errors other than by redoing the computation with much greater precision. That's the only reliable way to get an estimate of the effective round off. And it's expensive. Now, there are folks who say what you should do is change the direction of rounding at random from one arithmetic operation to another. And it turns out, that is, it's exemplified if you study the results on the previous pages, you'll see that there seems to be a lot of repetition in the variations that are exposed by recomputation with redirected roundings. And that's because it turns out that very often, very few rounding errors are responsible for the bulk of the variability. And so what that does is really undermine the central limit theorem. The central limit theorem of statistics doesn't work very well with rounding errors that are randomly generated, because the way they're randomly generated is by choosing either to round up or to round down. I mean, if you really wanted to make them random, well, then you'd have to have a lot more bits. But then if you have a lot more bits, why not use them systematically and try to get more accuracy rather than try to degrade it? So no, as long as the rounding errors are just redirected either up or down, the central limit theorem is very likely to be thwarted. Well, I'd like to move on now to a different problem. The different problem is simply this. We can't afford always to do recomputations. We can't afford always to compute things 4 times. We sometimes simply have to trust a computation that has been performed sufficiently often to make you feel that whenever you check it, it seems to be correct. Now, there were figures in the past, like Neumann, who really thought that computing with round off is just too hazardous. It cannot be reliable. In fact, one of my colleagues at Berkeley said that if you are willing to accept round off, then what you're really doing is acquiescing to a state of sin. We have succeeded in showing that some computations are overwhelmingly likely to be accurate to an extent that is predictable from properties of the data. But the trouble is that in many of these cases, there will be extraordinary situations where the error due to round off is enormously bigger than usual. And I'm going to try to show you an example like that, just simply so that you won't put too much faith in recomputing 4 times. It almost always works, but Sometimes it doesn't. Matrix inversion. Matrix inversion has been worked over many, many times. There are papers, for example, by Alan Turing and others who have shown that there is something called a condition number that usually determines the extent to which round-off is going to accumulate to degrade a computed result. This condition number near the bottom of the page, K of B, actually it's Greek letter kappa, is the product of the norm of B and its inverse. In consequence, the condition number turns out always to be at least as big as 1. It's 1 only for diagonal matrices and orthogonal matrices. It measures how close the matrix is to singular matrices. And if K of B is large, which means because it's reciprocal measures that angle, let me show you what happens here. Here's some idea of what the condition number means. The singular matrices, the ones that have no inverses, they form a cone. This cone intersects itself because the cone has matrices of rank 1 less than full, and it intersects itself along little cones, which are represented simply by a line here. The big cone of singular matrices intersects itself along matrices whose rank is 2 less than full. And further intersections occur. Now, an ill-conditioned matrix is extremely close to the cone. In fact, the angle subtended at the origin in matrix space, the angle subtended by the line to a given matrix and a line to the nearest singular matrix, that angle has a sign that's 1 over the condition number. For at least for the norm that we're using right now. The norm is the largest singular value norm. Now, it turns out that there is every reason to expect that the rounding errors that you commit will get magnified by the condition number, roughly. And so if a computed inverse is very, very inaccurate, we blame it on the data. We say, well, the matrix must be terribly ill-conditioned. And that's almost always true, but not quite. A counterexample is going to follow. Now, here is a family of matrices that are built up out of 4x4 blocks. The identity matrix that you can see in the diagonal and on the last column, that's a 4x4 identity matrix. And the matrix M that you can see just under the diagonal, that's a 4x4 matrix, all of whose elements are the same. Their values are just 2 units in the last place less than 1. And I'm going to use as the norm This is the maximum singular value norm. That's how I'm going to measure the error in matrices. So I'll measure the inverse by using that norm. Now that norm is convenient because, as you see near the bottom, if you transpose a matrix, you don't change its norm. If you transpose a matrix, you transpose its inverse. And the condition number of a transpose is the same as the original. So it's a convenient norm. So let's see what happens now. The matrix B that I've chosen has dimension 28. And that's because the next larger matrix with the same shape, the same structure, it turns out MATLAB didn't like it. MATLAB says, oh, it's very much too nearly singular. You see the reciprocal of the condition number for a matrix whose dimension is 4 times 29. You can see the reciprocal of its condition number is of the order of 10 to the minus 20. So that says the sine of that angle is of the order of 10 to the minus 20. That's very nearly singular. Okay, so we stop at 28 times 4. And so our matrix is of dimension 112 by 112. Now, the norm of the matrix and the norm of its transpose turn out to be the same. And when we compute the inverse of the matrix, that's E, and the transpose of the transposed inverse, okay, no, it's not the transpose inverse. It's the inverse. They're computing the inverse. It's not really the inverse. It's a computed inverse. And we compute the inverse of B transpose and then transpose that. So E and K ought to be the same, at least in principle, but they aren't. Look, E is about 7.5 and K is about 5 1/3. That's quite a difference for two inverses that ought to be the same. So round off must be virulent. Why do they differ by so much? If we look at their condition numbers, the condition numbers are about 40 or 30 odd. That's not very big. At least one of the E and K must be inaccurate. But it can't be terribly inaccurate if the condition number is not very big. And yet, they differ by an awful lot. That's very perplexing. Well, let's see. Let's look into this in order to get some idea of how inaccurate they are. What we're going to do is compute residuals. Now you see, if E is an inverse, look at this. If E is an inverse, then the residual, BE minus the identity, if E were exactly the inverse, Q would be 0. So if Q is far from 0, that means that E is not a very good inverse. And there's a different inverse here, R. That's just obtained by reversing the order of multiplication. And look at them. Instead of being 0, Q is around 12.5 and R is around 7. Those residuals are pretty big. They're very big for something that we wish were 0. And therefore, we can't infer anything much about how big the error is, other than that it's at least 2. The norm is at least 2. That we can infer. This computer likes to flip pages. Now, what about the residuals for K? Remember, K was the transpose of the computed inverse of the transpose. And so its norm is, really tiny. The 2 residuals have very tiny norms, around 10 to the minus 14. Actually, those residuals are not very accurate, because the rounding error that accumulates just when you compute the residuals is not going to be much smaller than that. So these residuals, you can't really trust anything except approximately their order of magnitude. You can't really trust the digits like 4 point something or 7 point something times 10 to the minus 15. No, you can only trust that it's around 10 to the minus 14 or 10 to the minus 15. But they are nice and small. And because they're nice and small, that means that you can get some rough idea of the error. How much does the inverse K, computed inverse, how much does it differ from the true inverse? And it turns out that there are formulas which allow you to infer that from the residual. This tells us that K is very accurate and E is not. Why is E so bad? Okay, I'll try to explain that now. The trouble with E is not so much that it's wrong as that it's not obviously wrong. Its ostensible condition number is not terribly big. And so if we hadn't done this computation of residuals, we wouldn't know that E was so bad. Of course, you'd like to have an explanation. Well, the explanation is something called excessive pivot growth. And so you can read this. It explains what's going on. But what really matters is that you've got to have some way to defend yourself against being fooled. And the way you defend yourself, you have to do to defend yourself against being misled is compute residuals. Even if the residual has no correct significant figures, if at least the exponent tells you roughly what the order of magnitude is, that will help you get some idea. And it's some idea of the error, but also it can be some idea of how to improve your result. The citation near the bottom of the page tells you how, by computing residuals, you can not only get an idea of what the error in the inverse is, but you can also improve the inverse. And that's very handy. And it's a general principle. If the thing you want to compute is defined by being the solution to some equation or equations, then calculating the extent to which your alleged solution dissatisfies the equations, because that's what the residual is, that can give you some idea of how inaccurate your alleged result is, and also some idea of how to improve it. So it's always a good idea to compute residuals, but it costs something. And so maybe you'll compute residuals for the first few instances of your computation. And when you feel satisfied that all the computation seems to be always reasonably accurate, then you might stop computing residuals, in which case the time will come when you're betrayed. Okay. Let's change the subject. What about overflow and underflow and other things? Well, it's a peculiarity of floating point, but that is shared with integers, that you only have finitely many digits. And consequently, you can only have finitely many finite computed values. And so somehow you're going to have to live with the fact that you may wish to compute something, maybe just temporarily. Maybe it's just an intermediate result on the way to something else. But the time will come when you have to compute something which is either too big or too small. And here's a simple example. You want to compute x times y divided by z. Now, actually, you don't really want to compute this as a final result. It's very likely that this is just a sub-expression on your way to something else. But what you would like, and you'd like very much, is you'd like to be able to compute this sub-expression provided it's not too big or too small. And so you now look at some hazard. You see, there are three ways to compute this sub-expression. They're in the middle of the page. If x and y and z can vary extremely widely, then some one or two of those sub-expressions may overflow or underflow, when the third is perfectly okay. And so you'd like to compute it in the perfectly okay way. But if you choose the wrong one, you're going to get an overflow or an underflow. And that can be somewhat annoying. Well, if you're convinced that this sub-expression, if computed correctly, would lie well within the floating point range, then what you really have to do is compute all three of them, or at least compute them in sequence and say, let's compute the first. You might compute them in sequence. Compute the first one, x times y, and then divide by z. Well, if that overflows or underflows, you'll discard it and go to the next. But that's possible only if overflow doesn't stop the computation. It's possible only if underflow, which just gives you zero, well, you might not think that zero is exceptional. How do you know that this doesn't deserve to be zero? You have to compute it a second time. So the process is compute x times y, divide by z, ask, has this underflowed? Has it overflowed? If so, discard it and try the next one. But if you weren't allowed to do that, if you couldn't test to see if overflow or underflow has happened, but rather if overflow just simply stopped the computation, well then, how would you compute this thing, assuming that it does deserve to be computed correctly, but if you get an overflow on the way, it'll stop the computer. That's how things used to be. Back in the good old days of roughly speaking, the late 1950s. That's where the IBM 650 used to live, in the late 1950s. That's what used to happen. Overflow would just stop the machine. So instead, we now have flags. And if you can test the flags, then you can tolerate the occasional overflow. It'll just simply be an excuse to do the computation in a different way. There are several exceptions that are prescribed by the IEEE Standard now. And they allow you to either trap and stop, which you might wish to do because you may say, well, if it overflows, then I like to rethink. So let's stop the computation. So you can either trap, stop, go somewhere else, or you can continue after accepting a pre-substituted value. If an exception occurs, you could say, well, if overflow occurs, actually any sufficiently big value is good enough. I'll be able to continue the computation if that big value is enough, because I intend to divide by it. So here are the options available to you. And the 5 floating point exception classes. Now, I've got to be careful because I'm using the word exception in a way that is different from people who program in C or program in Java use it. The word exception means something different to them, whereas the word exception means to me either a class of events, like overflow is a class of events, or it means the actual event. If overflow happens, that's an exception. Whereas in Java, an exception, the word exception means something that you do in response to what I would call an exception. Well, I just have to warn you that words mean different things to different folks. The default is something that used to be built into the hardware. Nowadays, you can probably get something more flexible if you insist. But the default, for example, for trapping, where does the trap go? Well, there used to be that the trap went to a specific place. And nowadays, I think you have some choice about where the trap would go, but it's usually the same for your program. You don't normally get to change it because the people who have produced the operating system are very jealous of jumping around with programs. And so they tend to be reluctant to allow ordinary programmers the opportunity to change the destination of a trap. And there is something like that that's allowed in a limited way. It's a set jump, long jump in the C. But set jump, long jump is a rather dangerous thing because there are questions about the scope. And so I don't think set jump, long jump is a good idea. And normally people try not to use it. Anyway, defaults for pre-substitution are also pretty straightforward. The exception flags that get raised, you can read this, you can see what it should do. It's pretty standard. But what should the pre-substitutions do? Well, for each of the 5 exception classes, there are things that are used to be built into the hardware, and nowadays you can probably get a different set of choices if you want to change the pre-substitutions. But the one that I want to talk about is inexact. Now, it's rather strange that we call that an exception, because almost every floating point operation is rounded, and it raises the inexact flag. Of course, it only has to raise it once, because only the first occasion of an exception raises its flag, and after that, you just leave it up. But the thing is, sometimes you want to generate data to test the accuracy of a program. And that means that you have to use formulas that will generate the data as accurately as possible, because you don't want the uncertainty in the data to contaminate your estimate of the uncertainty in the computation. The matrix A and M that we had a little while back, remember, for the vibrating structure, those matrices have elements that are integers, and although they are computed as floating point quotients, they're computed exactly. And therefore, you don't have to worry that the error in the final result is caused in part by uncertainty in the data. No, any of the error in the test result that we obtained is caused by the actual rounding errors in the course of computation. And that's the reason for having the inexact flag. For example, a least common multiple. We have to compute the least common multiple somehow. Well, if you don't have an inexact flag, then you don't know when the least common multiple is so big that it gets rounded. It's not the right integer. That's why we have an inexact flag. And there are lots of situations, but I don't have time to go into them now. There are lots of situations where you would like to know that something has been computed exactly without any rounding error. Well, there's a lot more that we should go into, but I've covered most of what we want for debugging floating point. Maybe on another occasion, we can talk about some of the other tools that could be used specifically for floating point, because you don't need them in other contexts. Well, that's the end.
All right, thank you very much. Let me applause. And we appreciate this very much.